Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll gather more intuition regarding how stiffness and mass determine the low and mid-frequency transmission loss of panels.
So let's get started. The stiffness per area, also called the modulus, and the mass per area of panels determine many important aesthetic and economic details about our choice for installing panels to stop sound between source and receiver. And understanding how both mass and stiffness affect the transmission loss guides many design decisions. At low frequencies, acoustic waves may cause a panel to vibrate in one of the structural modes, and this is a mechanical resonance phenomena. So we have our panel mounted over studs, and then when acoustic waves are incident on the panel, it might result in that panel vibrating back and forth as bounded between the two studs. Resonance primarily occurs around the lowest order resonance frequency, so we are often not concerned about the higher order modes of the panel. The damping of higher order modes for many common building materials is extremely high, so we neglect them. The transmission loss of a panel shows this dip at low frequencies associated with mechanical resonance, and the lowest order structural mode frequency is determined by the equation F sub m is equal to pi on 2 multiplied by d on m square root multiplied by a to the power negative 2 plus b to the power negative 2. And let's define these parameters. A and b are the height and width of a panel. The specific definition of which is height and which is width really does not matter. D is the bending stiffness. D is determined from an equation of y, the Young's modulus, multiplied by the moment of area, I prime, divided by 1 minus nu squared, where nu is the Poisson's ratio. So y is the Young's modulus as units of newtons per meter squared. I is the moment of inertia for this panel. I is equal to h cubed on 12, where h is the thickness, and nu, the Greek nu, is Poisson's ratio. Finally, we see m. M is the mass density per area. So m is equal to rho h, where rho is the density of the panel. This then is our Fm in the general trend of transmission loss of the panel. In the mid-frequency range, oftentimes the speech frequency range, we see that the transmission loss follows the mass law. The mass law is approximately equal to 10 log 10 of the quantity 1 plus omega m, the surface mass density, divided by 2 rho naught c, where rho naught c is the specific acoustic impedance of air. This quantity is squared, and then we close the bracket. According to our transmission loss trend for panels, in the mass-controlled region, the transmission loss changes by 6 decibels per octave. And if we double the mass, such as by doubling the thickness or density of the panel, we increase the transmission loss over the mass-controlled region by uniformly 6 decibels. So the resulting change would be something like this, where this vertical change would be 6 decibels. Similarly, if we reduce the mass by 1/2, by cutting the thickness in half, or using a material with half the density, we'd result in a uniform minus 6 dB change over the transmission loss in the mass-controlled region. And this mass change could be affected by either changing the panel density or thickness. And while enhancing the transmission loss in the speech critical frequency range is relatively easy to achieve by increasing mass, there are many, oftentimes hidden costs to increasing the mass of our chosen wall installation. For instance, increased mass is greater bulk material cost. It's greater shipping cost since it's heavier to move it from a supplier to a manufacturer. It will then cost more to ship that manufactured part to a distributor. And it would cost even more to install since it's heavy. And heavier things take longer to install. In the world of vehicles, increased mass reduces fuel economy for both aircraft as well as ground vehicles. It results in greater wear of the components. It results in longer stopping distance for automobiles. It reduces the quartering speed of the vehicle, and so much more. Although mass is easy to increase to enhance transmission loss, there are many costs to consider. To summarize what we've learned, the size, thickness, and density of panels are chosen to balance the cost with the transmission loss performance. The result from different factors including mechanical resonance and the mass-controlled sound transmission region. Changes in the panel mass by either 2 times or 1/2 times results in a plus or minus 6 decibel change of the panel transmission loss uniformly over the mass-controlled region. And there are great interests to find innovative ways to enhance the transmission loss in the mass-controlled region without adding extra mass. For instance, by exploiting acoustic resonance, laminated designs, shear damping. But these ways are fundamentally limited by the basic physics of bending wave propagation in the speech frequency band.
That's it for this video. In the next video, we'll look to the mid and high frequency range of transmission loss to learn more about the mechanisms of coincidence.